In this video, we're going to look at question 1 from, we're quite close to the end of the Strength and Materials course notes, because this is the section on learning outcome 3 about torsion of shafts. This is on page 51, the second last page of the course notes. And this question, we're given some information about a shaft that's transmitting a torque, and we're given some information about the diameter, the speed, the angular speed that is, and then limitation on how much twisting there can be, the length of the shaft, and also the modulus of rigidity as well. So we're given plenty of information about this, and certainly enough to solve this question. We're asked to find three things: the maximum shear stress in the shaft, the torque that can be transmitted, and the power transmitted as well. And we'll make a start by listing the information we have to begin with, but we'll make a wee note about question 1 there. This is the maximum shear stress. Well, the maximum shear stress will be at the maximum radius, which is simply the radius of the shaft, and we're already told that there's a limit of 1 degree in terms of the angle of twist. So we know that will factor into our calculation as well. However, we can take the same approach we would always do in such a question and begin by writing out the information we have. So we know that the diameter is 80 millimeters, and from that we can see the radius is, well, you would need to write this, but I'm being entirely explicit here, 80 divided by 2, which is 40 millimeters, and that of course is 40 times 10 to the minus 3 meters, or you could write 0.04 meters if you prefer. Yes, that's right. But however you write it, make sure you have it correct. You divide by 1,000 to convert millimeters to meters. We're told that omega, that's our angular velocity, is 140 revs per minute, or RPM if you prefer, and that's going to be equal to 2 pi times 140 divided by 60. That's the conversion factor from RPM into radians per second. We multiply by 2 pi and divide by 60. This is something that we cover in engineering dynamics, but I'm making it explicit here so that we can be clear. If we enter this into our calculator, I'll do so just now. I'm doing so to give you both the value as an exact value in terms of pi, but also the decimal value. So depending on your calculator setup, you might get something like this, 14/3 pi, which is entirely fine to use in your calculations if you want it to be more exact. Or we can write this in its decimal form, and the 3 decimal places is 14.661. Again, the units are radians per second. We're told that the angle of twist, remember theta is our symbol for angle, is 1 degree. And if we want to convert this into radians, we recognize that there are 2 pi radians in every 360-degree circle. These are both representations of a full circle. So 1 times 2 pi divided by 360 tells us the value in radians. And again, you could leave this as an exact value of 1/180, all multiplied by pi, or we can put it into decimal form. And again, 0.017, because it's such a small number, we'll take it to 4 decimal places, or 3 significant figures, 175 radians. We're also told the length of 3 meters, and pleasantly, we don't need to do anything with that. Meters are the units of length that we wish to work in, and we're given the value for G, the modulus of rigidity, which is 75 giganewtons per meter squared. And if it's 75 giganewtons per meter squared, that's the same thing as 75 times 10 to the 9 newtons per meter squared, because 1 giganewton is 1 billion newtons. I think giga means that you put 9 zeros after it, and we have 9 zeros after 1 is 1 billion, so 75 billion newtons per meter squared, or 75 times 10 to the 9 newtons per meter squared. So this is all the information we have from the question, and it's never a bad idea to write all this out and convert the units to begin with, because Very rarely will we give you a value in a question that we don't need somewhere. So let's turn our attention to part 1 then. We're asked to find the maximum shear stress in the shaft. Now in this unit, there's only one formula that we use that has shear stress in it, so that should be a big clue as to which one it is. And we'll find this on page 46 of the course notes. I'll put this in here just now. It's this formula here. It's our formula for doing our simple theory of torsion calculations. And we're going to use this in order to calculate the maximum shear stress. Now, I instinctively, based on the values I've seen popping up, I'm thinking we're going to be using a particular part of it, but let's just have a look. We don't know the torque and we don't know the polar second moment of area, although we could find polar second moment of area. But we do know everything here. We're given these three in the question, and we've already worked out R because we had a diameter, so we found the radius. So it would make sense here to use these two parts of the formula, and that's exactly what we're going to do. So we're going to say tau, and we can call it tau max because we're working with R max. Tau max over R max, but if you want to write it as tau over R, that's completely fine, is equal to G theta over L, and we can rewrite that as tau max is equal to G theta R max, you call it theta max there, divided by L. And we have all of these values. G is 75 times 10 to the 9. Theta we have converted into radians, 0.0175 radians, and the maximum radius is just the outer radius of the shaft is 40 times 10 to the minus 3, and this is all divided by L, or length, which is nice and simple, 3 meters. So we can put all of this into our calculators and come out with a value for the maximum shear stress. And if we do this correctly, we will have solved the first part of the question. And the answer that we get out here is, well, in the calculator, 175,000,000. And the units, if you weren't sure, for stress is force per area, but you didn't know which ones to use for this, they are given again the same page we found this formula, and they're in newtons per meter squared, because they're the units for force and distance we're working with. And of course, we could recognize that this is in fact the same as 17.5 times 10 to the 6 newtons per meter squared, or 17.5 meganewtons per meter squared. So a meganewton is 1,000,000 newtons, so we can replace the times 10 to the 6 with the capital M there. It means the same thing. But any of these answers would be fine, and you'd be perfectly all right with that. So that satisfies question 1. Looking now to question 2, we're asked to find the torque that can be transmitted. Now, there's two formulas where we encounter torque in the course. One of them is this one here. I'll make a copy of it down so we can look at it. This one here, we can find torque, and we've got another formula involving angular velocity, which we know, but in power, which we don't. So that tells us we can't use that formula for power, but we will be coming back to that. So instead we use this formula here. And because we worked out stress in the last part, we actually know everything in here and everything in here. So we could choose to use either of these in combination with torque over polar second moment of area. But we're not going to use the middle one. And the reason for that is because we calculated shear stress in the first part of the question. And there's always the possibility that either we've made a mistake if we're working on this in an exam condition, or we have rounded and we will show for accuracy. So we're going to use the values that rely on a lower level of calculation. So the G, theta, and L are given to us in the question, so we're going to use these. We need to find torque, so we need to use T over J, but J is something we don't have. So we need to use something else from the course notes and find the polar second moment of area for this particular shaft. Now, looking at the question, we're told it's a solid shaft, so we don't have to work out what's going on here. And the course notes gives us a formula for polar second moment of area for a solid shaft. We find this on page 48 of the course notes. So I'll make a note here. Page 48 tells us the polar second moment area of a solid shaft is found by pi times the diameter to the power 4 divided by 32, and that our units will be in meters to the power 4, assuming we're using diameter in meters. This means that J is going to be equal to pi times, well, our diameter is 80 millimeters, so that's 80 times 10 to the minus 3 meters. That whole thing is to the power 4. So if you find it easier, you can put 0.08 to the power 4, or put this bit in brackets, but make sure the whole thing, 80 times 10 to the minus 3, is to the power 4. And divide this by 32. And it's easy to make a calculator mistake, so we'll do our best not to. Here's everything: pi multiplied by, and I'm opening brackets, 80, pressing the exponent button, the times 10 to the x button, minus 3, closing brackets, raising it to the power of 4, and dividing that whole thing by 32. And the value I get out here is unsurprisingly quite a small number, because we're taking a small number to the power 4 on the top of our fraction. We get 4.021 times 10 to the minus 6. And of course, the formula tells us already our units are meters to the power 4. So now we have everything we need to solve this. We can say that torque is equal to G theta times J, this time over L. And there's some repetition of what we had before. G was 75 times 10 to the 9. Theta, well, I can't remember that off the top of my head, so I'll go back up with 0.0175. J, we've just worked that out above, it's 4.021 times 10 to the minus 6. And that's all divided by L, which is 3. So we'll calculate this just now, and from this we'll find the value for our torque. And the value we get out here, the calculator, 1759.1875 based on my numbers. And of course, units for torque are Newton meters because it's force acting at a distance. We'll compare that to the answer here. The course notes came out of 1755, we've got 1759. This is the sort of thing you may experience depending on how you've rounded. I suspect it's because I rounded J to 4.021 times 10 to the minus 6 rather than 4.02. So we'll say this is close enough, but we can probably say it's accurate enough to say 1759 Newton meters. So don't be overly concerned when you're doing tutorial questions if there's a slight variance in the answer. Remember, this represents less than half of 1% of a difference in the answer. So we won't worry too much. We know we followed the method correctly. And I'm sure you can manipulate your rounding in such a way that you would end up with the same final answer. And the last thing we're asked is to find the power transmitted. Now we're told about power again in the unit, and this is slightly earlier on, but we do come across it. And the formula for power is given on page 44 of the course notes. And power is equal to torque times angular velocity. Well, we know both torque and angular velocity, so it's simple as saying power is equal to 1759. So I'm using my value, so the final answer will be slightly shifted due to that. And I'll use the value for omega. Remember, we wrote it down at the start, it's 14.661 radians per second, because we converted that speed from RPM. And if we enter this into our calculator, we'll get the final answer on the final part of this problem. And we can compare it with the course notes and see how much we've deviated from them. And the answer that comes out here, I'll write in the calculator value. First of all, is going to be 25788.699 watts, or 25.8 kilowatts. I can divide by 1,000 to convert it to kilowatts, because a kilowatt's 1,000 watts, so 25.788699, and I round it to 25.8 kilowatts. And we can see that's exactly what the answer is in the course notes. So despite the slight difference in rounding that we got to get our answer for torque, it's evened out because of such a small difference when we get our answer for power at the end. So that's the answer to question 1. There's other videos coming which will show the other tutorial questions in this section of the notes.